Let's continue our discussion of the link layer by moving on to switch local area networks. So far, we've already seen addresses used by hosts and routers, which take the form of 32-bit IP addresses. These are used specifically at the network layer level. However, at the link layer level, we also have addresses for both hosts and routers, and these are called MAC or LAN or physical or Ethernet addresses, but we'll stick to just calling them MAC addresses, medium access control. And what these are used for is to get frames, which are what's sent across the link layer level from one interface to another, usually from a physically connected interface. So if you, for example, have the same network, you wouldn't be using IP addresses to figure out how to get from one interface to another. You'll use a MAC address. And so a MAC address, unlike an IP address, is 48 bits. And so it takes the form that looks something like this in hexadecimal form. Each of these characters represents 4 bits, so it's basically 6 bytes. And these addresses are typically burned directly into the network interface controller. Originally, these were intended to be permanent. However, there now is software that can change these if you need to. So here's just a brief look of what that might look like. You have a local area network here, which could be wired, could be wireless. Each of these devices has its own adapter, and each of these adapters has a unique LAN address or MAC address. But how do you make sure that these MAC addresses are unique? Well, the IEEE is the body that's responsible for administering all of the addresses, the MAC addresses that are out there. So if a manufacturer wants to build these interfaces, they need to buy a portion of the address space that's included in MAC addresses to ensure that they're making unique choices. You can think of it kind of like how each person has a unique social security number. My social security number is distinct from everybody else's out there. And so that means that you can move from one LAN to another, and your MAC address is still unique. However, an IP address is more like a postal address, postal code, that kind of thing, where it is not portable. What my current postal address is depends on where I live. So right now I have a different address from when I used to live back in Oshawa, but my social security number did not change while I made that move. So the obvious question then is, if you know an IP address, how do you get the MAC address out of that? And the way that it's done is through what's called an ARP table, Address Resolution Protocol. So each node, whether it's a host or a router on the network, is going to have a table, and the table maps IP MAC addresses for some of the nodes, and it includes information that looks something like this. You have IP address, MAC address, you know which one's for which, and TTL, time to live, we've seen this before, which is the time after which this mapping of addresses will be forgotten, and it's typically about 20 minutes. So what does the ARP protocol look like for devices on the same LAN? Suppose you have one node A, which wants to send a datagram to a node B, and B's MAC address is not in A's ARP table. What does it do? What it does is A is going to broadcast an ARP query, which contains B's IP address. And so the destination MAC address is going to be just all Fs, that's basically all bits set to 1, saying that I don't actually know what this MAC address is, someone please tell me. All the nodes on the local area network are going to receive this query, including B. And when B gets the packet that's asking for its MAC address, it replies directly to A with its MAC address. And so that way now, and using it unicast, it's going to have a frame directly sent to A, and now A is going to know the information that it needs. A is going to save this address pair in its ARP table until the information becomes old, so time's out. Maybe that's after 20 minutes. Maybe a refresh happens if you are using soft state. And ARP is plug and play, which means that each node is going to create its own ARP table without having some administrator determine what the table is going to look like. Let's talk a bit about the Ethernet. So Ethernet was once upon a time, and probably still is, the dominant wired LAN technology. Maybe this video will come out of date real quick and we'll see, but definitely for a long time, Ethernet was the way that you connected to the internet. It uses a single chip that has multiple speeds, depends exactly on what technology you're using for it. It was the first widely used local area network technology. I definitely remember when I was young growing up, Ethernet is what we had to use to connect all the computers in the house. Simple, it's cheap, and it's actually kept up pretty well with the speed race in terms of how quickly you can actually transfer information, ranging from 10 megabits per second to 10 gigabits per second. So here's a quick picture of Robert Metcalfe, famously known as the co-inventor of the Ethernet, and his original sketch of what the Ethernet might look like. So here we have this cord, this coaxial cable that runs along a bunch of these different devices here. And near one side of it is where you have your interface controller, the thing that actually handles all of the working on the internet with your devices that are over here. So popular through the mid-90s was this bus approach to the physical topology of Ethernet. So here you have each of your little devices has a coaxial cable that runs along all of them, and each device connects to that little cord, basically meaning that now all your nodes are in the same collision domain. They can collide with each other. Not really great, which is why today we have more likely a star topology when it comes to the Ethernet. So you have this active switch in the center, and each spoke runs a separate Ethernet protocol, so you don't have to worry about nodes colliding with each other. And so right now I have this running, for instance, in my room. Over there is my router. It's got an Ethernet cord that's running all the way to this device, but I also have other devices that are connected to that. For instance, my phone right here is running on the wireless that's coming from that router as well, and I don't have to worry about the collisions between my computer here and my phone. So let's break down the contents of an Ethernet frame. So Ethernet frames are going to encapsulate IP datagrams or whatever other network layer packet that you're dealing with. And the sending adapter is going to do this encapsulation, including basically everything you can see here. So one step at a time, let's start with the preamble. The preamble is 7 bytes that all have the pattern 10101010, followed by one that's the same but a 1 at the end instead of a 0. And the point of this is that consider that Ethernet, although it may advertise that it travels at 10 megabits per second or 100 or 1 gigabit per second or whatever, in reality, it's never exactly the number that it says. There's always going to be some amount of variation there. So the idea behind this preamble is that when the receiver starts getting this frame, they can sort of get this as a wake-up call to say, oh, look, here are these just initial bits that are just going to be alternating. Here's my chance to kind of wake up and realize, oh, there is something being sent to me. Let's synchronize our clocks to make sure everything is okay. So the other contents of the frame include the addresses, source and destination. These are MAC address, so it's 6 bytes, 1 for source, 1 for destination. If an adapter receives a frame and the destination address is matched, or if it's a broadcast address, so remember this is the all Fs, then it passes the data in the frame to the network layer protocol. If it gets the wrong address, like something that's meant for something else, it just discards the frame completely. Type, which is stored here, basically just indicates what protocol we're talking about. Usually it's IP, but there might be some others that are available. And then finally CRC, that's the cyclic redundancy check done at the receiver to make sure that there are no errors. If there is an error detected, then the frame is dropped. So some more properties of Ethernet. It's unreliable, it's connectionless, so that means there's no handshaking between sending and receiving controllers. The receiving controller doesn't send acknowledgements or negative acknowledgements. Any data in the drop frames is recovered only if the initial sender uses a higher later reliable data transfer like TCP. Otherwise, any drop data is just gone. And then for MAC protocols, it uses unslotted CSMA with collision detection with binary backoff. And you can go back a little bit if you forgot what that is. Now, when it comes to Ethernet, there are a lot of different standards that are out there. They are common in terms of their MAC protocol and their frame format, but there's lots of different speeds that are out there, maybe 2 megabits, 10 megabits, 100, up to 40 gigabits maybe. There are different physical layers that can go on here. So we have copper twisted pair wires for some, we might have fiber for others, and basically there is some variability in terms of what goes on with Ethernet standards. Next, we'll talk about switches and virtual lanes. An Ethernet switch is a link layer device that takes an active role in storing and forwarding Ethernet frames. Like we kind of discussed already, it looks at the MAC address of an incoming frame, figures out where it's supposed to go, and uses CSMA with collision detection to access segments. Compared to traditional hubs just transmit all the bits at the bit layer. Switches are a little bit smarter with regards to how they handle things. Hosts are completely unaware of the presence of switches, and they're plug and play, which is extra useful, meaning that you don't have to configure them at all, you just plug them in and they start working right away. And they're self-learning as well, which saves you a lot of work if you have one in your home. So here's a quick look at some Ethernet devices that are out there: switches, splitters, and hubs. Splitters basically would take 2 Ethernet cables and combine them into one on the other side, which then you have to unsplit if, for instance, you want to connect 2 devices in one room to a router in another room. Hubs, meanwhile, aren't as intelligent as switches, is perhaps one way to put it, in that they generally just broadcast information all about without thinking too much about where information actually has to go. So this is where you might plug in your connection to the internet along with all your other devices, and then messages are usually sent with a half duplex passages, meaning that you can't really have information going two ways at the same time. Most of the time these days you're going to see switches as the center of most local area networks, which are, as I described already, somewhat more intelligent, self-learning, and plug-and-play. So unlike a hub, an Ethernet switch allows hosts to have their own dedicated direct connections using full duplex. The switches can buffer packets that are used to transmit, and each incoming link uses Ethernet protocol with no collisions. So each link here is its own collision domain. You don't have to worry about what's happening from A to collide with what's happening from B. When it comes to switching, so instance you want to transmit something from A to A apostrophe, A to A apostrophe and B to B apostrophe can all send directly across with no collisions actually happening, because they're all different devices with their own different links. Now the big question is, how does a switch know that it reaches A apostrophe using interface number 4, or that B apostrophe is reachable through interface number 5? The answer is that each switch has its own switch table, the entries of which contain the MAC address of each host, the interface to reach the host, and the timestamp. So it looks kind of like a routing table. But now this begs the question, how are entries created or maintained in the switch table? Do we use something like a routing protocol? Let's take a look. As I previously mentioned, switches are self-learning. So the switch is going to learn which hosts it can reach through the different interfaces that it has. When it receives a frame, the switch learns the location of the sender. So, if A is going to send me some frame, then I know that 1 is the interface that handles A. And it's going to record the sender location pair in its own switch table. Let's take, for example, A has a source of A and a destination of A apostrophe. The switch table, which initially starts out as empty, is immediately going to be updated once this frame gets sent out to say that the MAC address of A is what it is. It's coming from interface number 1, and the time to live is 60. Let's say 60 minutes, and then we'll get rid of that and need to update it. Let's take a look at how switches handle filtering and forwarding different frames. So when a frame arrives at the switch, the first thing it does is it records the incoming link and the MAC address of the host that sent the frame. Then it checks its switch table to see if it can find the MAC destination address there. If it's there, then there's another check that needs to be done. Is the destination the same interface that frame just came from? If so, that means this was probably broadcast already, and we can just filter or drop the frame. If the destination is different from the sender, then you forward the frame along the interface indicated by the entry in the table. If the table doesn't have an entry for the MAC destination, then you forward on all interfaces except for the one that already sent the frame out to try to figure out where that destination is. Let's take a look at an example of this self-learning and forwarding. Suppose once again we have a frame that we want to send with the source of A and a destination of A apostrophe. Our switch table starts out as empty. And at the beginning, we don't know where A apostrophe is. The table doesn't have an entry for it. So what do we do from that? We flood. We send out to everybody, hey, we're looking for A apostrophe. Are you there? A apostrophe is here, and so it sends a frame back. You might actually just have the destination to be itself, and then once this frame arrives at the switch, then it can add the information from A apostrophe to the table to say now it's on interface 4 and it knows where it is. In another example, if the destination for, so for this case, if we're sending something to A is known, then we can just selectively send exactly what we want along interface 1, which is the one we know is connected to A based on the table. And we only do this on a single link. We don't need to broadcast things out because we know exactly where we're trying to go. Now, it's probably unsurprising that self-learning switches can be connected together. So you can have one self-learning switch here that's connected to another switch that connects two more switches, and each of these can be self-learning. So if I want to send a frame from A over here to G over here, how do these switches know, specifically the first switch, that it needs to send to S4 in order to get to 3 in order to get to G? And the answer is self-learning, which works exactly the same as the case of a single switch. Now, how does a switch compare to a router? Both of them have a few things in common and a few differences. First off, both of them are store and forward. However, routers work at the network layer. They look at the headers at the of the datagrams, while switches are link layer devices, and so they look at the headers of frames. Both have forwarding tables. However, routers compute their tables using routing algorithms, using IP addresses. Meanwhile, switches learn their forwarding tables through flooding and through learning MAC addresses. And you can see in this little diagram exactly the path that data might go through to get from one host to another, passing through a switch here and a router here. The switch handling data only at the link and physical layers, while the router is handling stuff at the network layer level. Let's talk about virtual local area networks. Consider the following problem. Suppose you have over here your school's network, and you're in the CS department over here, but you want to move your office towards electrical engineering. But you still want to connect to that CS switch over here. It's really handy if you're talking to the other hosts there very often. Well, what kind of problems do we have? First off, all of the layer 2 broadcast traffic, that's things like doing address resolution protocol, DHCP, trying to figure out where MAC addresses are, all that's going to have to cross through the entire local area network to do that. And there are also issues with regards to security, privacy, and efficiency. One way to solve this problem is with switches that support virtual local area networks. And so these switches can be configured so that they have multiple virtual networks over a single physical structure. So here you might have a single physical switch which is divided into 2 parts. So that way those in electrical engineering who use ports 1 to 8 are separated those from CS who use 9 to 15. And so what ends up happening is it's sort of like you have multiple switches from a virtual perspective split into half on one side, half on the other side. So what benefits does this offer us? First off, we have traffic isolation. If you are in the left half of things with electrical engineering, your frames can only reach the other ports that are there. So if you're on number 1, you can only reach 2 up to 8. You can also define the virtual network based on the MAC addresses rather than the switch port if you feel like it. Dynamic membership is also a benefit. If you just decide suddenly that whoever is over here at port number 3 should actually be in the CS domain, you can just decide that, all right, instead of it going to be ports 1 to 8, now it's 1 to 8 except for 3. That's going to actually be part of this virtual network. You also can do forwarding between your virtual local area networks, and this is done with routing just as you would with separate switches. In practice, vendors tend to sell combined switches plus routers, but you may find them separately as well. Just to summarize what we've talked about with regards to the link layer, we looked at the principles behind the data link layer services. So this is things like how error detection and error correction are handled, how is a broadcast channel shared, how do we do multiple access, and how do we address things at the link layer level. We also took a quick look at instantiation and implementation of some of the link layer technologies. We looked at how Ethernet works, how switches work, the differences between those and hubs or splitters, what a switched local area network looks like, as well as virtual local area networks.